It is Phil Bessle Day, and he is here as he should be. And Phil is here. I understand you're now a number one Amazon number one best-selling author.
I am. It should be privileged to know me, Randy. Oh, you are one too, apparently.
Apparently, nine of us have
Nine
become,
of us.
and in several categories, not just one
Yeah.
category. Usually, my goal is to make number one best-selling maybe the first week in some little tiny weird category that but we're number one under under artificial intelligence. I mean, that's pretty good.
That's what the book's about. So.
No kidding.
Yeah, yeah, yeah. It was really fun to write. I wrote one chapter, by the way, on data and something I know about. So that's like good. I mean, I remember you saying, "What chapters would you like to write?" And I'm like, I can't lean in on these other chapters. I want to focus on the data chapter, which I lived a life of data at Rivian, so I felt like, oh, I have something to say here. But yeah, it was really fun writing it, and it's so contemporary to the realities that we're living. Like every time I think about it, I'm like, well, we're gonna have to do a part like maybe we should do it AI Rising V 1.1 and then just go in and make changes because
it's so fast.
We have to revise things. Yeah.
I was looking at stuff that was coming out the day we were publishing and
and you're like, oh my God, what are we?
All right. So today, speaking of things that are changing, so 2 years ago, we didn't have memory. In fact, maybe a year ago, we didn't have memory in our AI systems. And now we have memory, and it's how do you get along without it? The next step apparently is reasoning. And I'm all about reasoning. I hope maybe the fan base would disagree with that, or even my mom might. So let's though talk about how FSD and reasoning are part of our futures.
Yeah, let's do it. And I have a presentation.
Oh, a presentation. Oh, wow.
Yeah, because I can't.
You just can't stand not being as good as CERN.
Exactly. That guy. And I've told him I'm gonna one up him, so we'll see.
Right.
Yeah, good luck. Anyway, yes, I do have a presentation, and so let's get into it. So let's okay, there we go, and slideshow. Yeah, so I want to talk about FSD version 14, and as we've talked about it a lot, but I want to talk about the reasoning aspects of it, and we're going to get into that in terms of what happened at Tesla in the last 2 weeks. First we had an earnings call. Well, in 1 week, I should say. Last week. Geez, this week.
3 days ago.
3 days ago. 3 days ago, there was the earnings call. Elon spoke about this a bit, and Ashok Elluswamy, his VP of AI, spoke about it a bit, and then Ashok dropped a presentation on FSD a day later, I believe, and then he did an article, which was and I think it was very, very well done, and it took me some time to parse it, and there's a lot in it, but instead of going into all of it, I want to talk about the aspect of reasoning, which he brought up. So first part of this right here is, I think I want to lead out with kind of a lean back. I want to say that so I wrote this article called I wrote this series of articles called The Magic of FSD. I just dropped part 8 2 weeks ago, prior to all this stuff, and it's called Optimus Edition, and it's a little odd to say what FSD, and what I was essentially saying is that FSD and the Optimus AI are the same AI. They're the same thing, or they will definitely be. They are converging to be the same unified architecture. And I just put a tease of that on the left here. This is actually a slide from Ashok's presentation at the ICCV. This is the international conference on computer vision. Apparently this happens every so often. And he presented there, I think, largely as a recruiting event, frankly. That's, I mean, because the whole back end of it is, come to Tesla if you're interested in doing vision AI. But what's cool about that picture there is that's a completely simulated view on a baseline of data that Optimus recorded. So using their same simulator that they use for several different purposes within FSD, they're able to simulate Gigafactory floor through Optimus. So that's all virtualized. That's not real. That came from real data. It's a real-time generative simulator system that they have. And so the message here is, that these AIs are unified. So if you're interested in FSD, this is a good presentation to talk about the reasoning aspects. But if you're interested in Optimus, this is also a good presentation to learn about the reasoning aspects, because frankly, I see them as the same thing.
Right.
Okay. So this is the article that Ashok dropped 2 days ago, I believe, Thursday maybe, or was it Friday morning?
I think it was Thursday. Anyway.
Yeah, I think it was Thursday overnight. It's a good article, and it's essentially the written version of the presentation. So the link to the presentation is below, where he talks through a set of slides. But frankly, I think the article is somewhat better anyway. Anyway, you have two places to go, and the title of his is the Tesla's approach to autonomy. Okay. Now, here's what he's saying, and this is how we'll kind of move this towards the aspect of reasoning in a minute. What he's saying is that their approach is that they built an end-to-end model, the neural network. And this is sort of interesting because there's some philosophy boundaries here that we should talk about. What an end-to-end model means is that essentially what you see here is on the left, you have the input data, cameras, navigation, the vehicle kinematics, the kinematic data, audio, and some other things that they aren't willing to tell us much about as their input. And this runs through on the car at what we found out to be 36 hertz, so 36 times a second. They run this data through this model, and they produce next action. And what's really, really fascinating about this is that on the left is effectively what he characterized as 2 billion tokens as an input stream. And on the right, 2.
Oh boy.
2 billion to 2, right? The 2 are steering angle and accelerator. So if you think of it, the positive accelerator,
negative, yeah.
Negative is braking. Frankly, I think there's a bit more than 2 because there's other outputs, but essentially 2 billion to 2 through this one unified end-to-end. So why is it end-to-end, and what does that mean? Well, the whys he peels apart in the entire presentation. Like, why are we doing this? Well, what does it mean? It means that the interior of this neural network is not just straight out a bunch of layers. It is componentized. There are modules inside. There are elements that do certain things, and I've characterized it in some of my articles as a mixture of experts architecture, which it is. But what he's saying is when we train, we run it through the entire thing. We don't train a module separately, connect it, what they call the modeler, what people would call the modeler approach, and then connect it to another module, and so forth. They train it as a whole, and that allows it to be, very, very nuanced and in its ability to predict next action. But there's a problem with it. And the problem is that most people don't tackle it this way because it leads to opaqueness. Like the model itself, it's like, oh, I see the data that goes in one end and I see the outcome, the action outcomes over here, but I can't see in the box.
Yeah.
And if I can't see in the box, I don't know what's going wrong when something goes wrong. But they figured that out. They figured that out.
They figured out how to get into the box.
Yes. They generate, through the model, they generate what are called intermediate tokens. So and we'll talk about that. So then he jumps into this whole idea of, if we built this end-to-end AI, pixels to control, right? The input data is largely vision data. I mean, of that 2 billion input tokens, at least 90-something% are vision camera data. And then the output is what we call controls. And he says, well, what are the main challenges? And he goes into 3 areas. The first area he talks about is the curse of dimensionality. Talk about that in a sec. Then he talks about interpretability and safety guarantees. And then he talks about the hard part, evaluation. Evaluation is kind of like, how does the model figure out what to do to make the decisions necessary? The curse of dimensionality is super interesting. And we're just touch it lightly here because we could take, pretty much a couple hours on this whole topic. Curse dimensionality kind of relates to 2 things. The thing I already talked about, which is they have 2 billion input tokens, and they're trying to reduce that to 2 output tokens effectively. That's a really high dimensional problem. And the curse of it to them is that it's, I guess you could say it's a 2-sided coin here. It requires a heck of a lot of compute, both on the training side as well as the inference side. So to do this their way requires an enormous training cluster. Guess what? They have that.
Yes.
Or they built that. They built it because they knew that they essentially had this curse of dimensionality. And it also requires a lot of inference compute resources. So, pushing the envelope on what the hardware 4 chip can do and why they're doing an AI 5 chip. And it leads into that. The curse of dimensionality also refers to the amount of data that they have. And Ashok said that they literally have a Niagara Falls of data. And it's so much that it's effectively they're recording or they are receiving in the data center 500 years of driving data every day. Yeah. Now, I'm not sure.
And that's just the data that they get because they're not getting every minute of every drive. They're just getting the ones that people are.
Yeah, it's what.
Yeah.
Yeah. It's what they've selected, and they use an enormous number of techniques. And he talks about that in the curse of dimensionality of how do we select the data we need to move to the data center? Because if we moved it all, it would swamp. It would take up 50% of the internet every day.
Right.
Yeah. And then he talks about interpretability and safety guarantees and what interpretability. And so we're going to talk a bit about the box of interpretability. And that really means is like, can you interpret what the thing is doing? Can you figure out what the thing is doing? That's what I said before is if you build this end-to-end neural network, you can't really see in the box. And if you can't see in the box, how do you debug it? How do you see what it's doing? So they figure that out for themselves to make it work. And it has this beautiful output, which we'll call reasoning in a moment. And then he talks about evaluation. And that's a big topic that we're not going to cover here. But it's like, well, how does this thing make these decisions that leads to driving?
So back up with me for a minute on interpretability. 2 years ago, a year ago, when we were first introduced to ChatGPT, it was 2 years ago, over 2 years ago now. Is it almost 3 years now? Anyway, we were first introduced to ChatGPT. Yep. And for those who are paying attention, there was all this conversation about we don't know how it's doing what it's doing. Is that because they weren't able to get into this box? Is that part of the problem?
Yeah, I mean it's a bit difficult. What you have when you have a neural network, what you're left with is a big box of numbers. It's not code. It's not, if we look at kind of the two worlds of this in terms of systems that build function, one system is algorithmic, where we as computer programmers write code and it's logic, and we can walk through it visually, and we can interpret it, and we can run test cases through it, and we can look at code coverage, and we can walk back to the line of code that may have caused the bug and fix that line of code. But if you have a couple billion parameters that are just numbers, real numbers, 1.26 and 3.89, and they're sitting in this layered neural network, which one's wrong when it makes the wrong decision, or which million of them are wrong or slightly wrong? Slightly wrong. It's a really hard problem. And the way you can think about it is the way it gets fixed is that you have to have the system as a whole kind of tell you through its runtime meaning the inference. It has to be able to output kind of what each of those block layers, if you consider it as a componentized or set of things, each of those blocks, before it gets to the finish line and tells you those control values, it has to output those intermediate values so that you have some way of understanding how it came to that conclusion. And in fact, it's a way to narrow it down, but not get to some, it's not a way, there's no way to say parameter in layer 4, parameter 16, the value 1.2 should be 1.26.
Yeah.
There is literally no way to do that. Yeah. And by the way, if that were to occur, you change that one value, that would set off other values in the wrong direction as well. So they have to be adjusted appropriately. It's not a problem that gets solved that way.
Right.
Yeah. Okay. So this is sort of the outcome of that. This is his slide in the section on interpretability and safety guarantees. What he means by safety guarantees is kind of like, if this is how we know whether the system is safe. It's introspective. We can look inside the box and we can see what it's done. And so what he's done here is he's expanded the large neural network into this other section he effectively calls reasoning. So remember before, a couple slides ago, all we had was the input and the action.
Right.
Now we have panoptic segmentation, 3D occupancy, 3D Gaussians, language, ... Now we could go through each of these, but what effectively is going on here is this is a system now that can output reasoning tokens. These are the reason why. If you reasoning as one concept is sort of like the whole process of thinking.
Mm-hmm.
But another way of thinking about it is it's just the outputs of the thinking. So this is why we would characterize this as reasoning tokens. We output the reasons why in these areas, like why did we see, what happened here? Well, we saw lane lines, so like 3D occupancy, for example, this is a way occupancy has nothing to do with vehicle occupancy. This is in the 3D space outside the car, visualized by the 8 cameras seeing 360 degree. What is occupying that space beyond just the fixed objects, like the roadway surface and so forth? Like, in other words, it's the stuff that I can't hit. It's the obstacles. It's the stuff.
Right.
Segmentation is a way of saying, let's break this down into all the little elements inside. 3D Gaussians is referring to the idea that we can we both reconstruct the three-dimensionality of the space. In other words, think about it. The camera is just delivering to you a 2D pixel diagram. Now, when you look at it, you see, the human, interpret it with depth, a depth perception.
Yep.
But if you just think of it as a bunch of pixels in a two-dimensional, there's no depth. It's just the color of a pixel. So what does that? Our brain's doing that, but their neural network is also doing that. And it can reconstruct that 3D space almost like it's looking down on the entire space and reconstruct it. And there's a great video that he shows in his presentation where he shows this red Tesla running down a street. And he shows like panning and zooming away from the car and looking at the entire scene. But the point is, that's what the car is seeing. It's not some drone looking. It's reconstructed literally from what the car is delivering to their system.
Right.
And that's what the inference system is doing that. So it's outputting these so-called reasoning tokens. The reason I saw what did I see? And then of course you could ask for interpretability, which is the whole point of evaluation. And then they've added this other thing. Let's go to this slide, which last part, language. Well, oh my God, what's going on here? Well, they've essentially added a mini language model inside of FSD. And here's the best slide to illustrate that. This illustrates a couple things. This is the debugging tool that they have. And they say in the first, so there's a chat, and they're chatting with the running FSD. And ego is the car. Okay, ego is a nickname, but it also, refers to the self.
Yes, yes.
And so when you think of, whenever you hear the term in this scene, the ego that's referring to the car, the actual object that's, recording the sensor data and trying to navigate the scene. So here we have a situation where we see road closed and there's a detour sign, and you can see that beyond there's a pretty serious road closed barrier. And so the first question is asked, there's a question asked of the system, can ego drive straight ahead to follow the navigation route? And it says, no, there's a detour sign and a construction barrier. And note that those things are notated in this thing in the green and the purple.
Yeah.
And they're labeled on screen. So what it's saying is this system has recognized both of these objects, and it's using both of these objects in its determination or evaluation of why it cannot go straight.
Right.
The next question is, how should ego get to its destination then? And it responds, ego should turn left at the intersection, which is above, and I mean, you don't see it labeled, it's here. And it says, well, why should, or the person asking, why shouldn't ego turn right to reroute? And it says, because the detour sign says to turn left. Now, it is plausible and it is possible that you could turn right.
Yep.
And it may, of course, reroute you and things may work out well. But in this case, it's saying, I'm going to rely on the detour sign to, in evaluation, I'm willing to rely on the detour sign to give me the proper routing to get around this road closure. So what's really fascinating about this here is the first time we've got to see a little bit inside what they're doing, and what we can see is that this runtime, this inference system, is able to answer questions about its evaluation model. So that clearly leads to the idea that we can do a much more expressive reasoning type of interactions with the system, which we'll talk about in a minute.
So how different is this from Grok, where I've got mine on permanently on the slow method of it whatever they call that, I forget now. And you watch it, and it says, I went up and I checked this on the internet, and I didn't get what I wanted.
Right.
So now I'm going to go check on this, this what do you call it? This government resource, and see if they've got any good information on that. Well, no, they didn't have any good information either. So now I'm going to go. Is that kind of similar to what we're talking about? Okay.
It is similar. It is similar. It's in this case, it's outputting its reasoning tokens, and it's saying that, and it's showing that, I'm running down this path of doing this this research. I find a reference to this resource. I'm going to go look up this data. I'm going to then in a kind of multi-segmented way, multi-segmented kind of reasoning model, I'm going to take the data I have and shove it back through the context window. It's a very good analogy, because what happens in Grok or ChatGPT or others is that you start with a prompt, what's known as a prompt, and what color is a stop sign, and or you ask some other research question, and it goes into a bit of a planner that tries to determine, can it answer that question from one pass through or does it have to segment it? And if it has to segment it, then it can then go run those little research elements maybe in parallel. They don't have to be serialized necessarily. They can go run off on their own GPUs, and they can come back and collect the data. And every time it's collecting the data from some component of research, which is either, let's say it does a web search for something, or it looks over, or Grok looks over the corpus of X, the body of material that's in X, looking for, because it can give like real-time expression of, if I write a post 10 minutes ago, it can appear in the results.
Right.
And that's not because the model's been trained with my data. That is because it has taken my data, it looks within X, it gathers the data, and then it has another segment or another part where it puts my data back through the context window. It's kind of a hidden part of the prompt. Goes and interprets it. This is similar in the sense that what's probably happening here is that it's holding those reasoning tokens internally with some memory. So not only can it explain how it did the evaluation, like they record the outcomes of that, but they also record the steps. So there's a bit of a history window that, I think of it as a sliding window, right? You're driving for 5 minutes, and they're sliding this window of history 30 seconds.
Yeah.
Right. And he talks about in his presentation, the 30-second window. So, on the 31st second, you trim off the first second, so forth. Right. So it's sliding. And that window is only as big as they can kind of hold in memory. It's a memory problem, right? Ultimately, it's a memory and compute problem, because if you have so much data in this window, you're kind of on the next inference cycle shoving a good portion of it back through the inference.
Yeah.
Or a summary of those things. And so what that means is that now you have more compute for that cycle.
Right.
And he talks a little bit about that early on. He says that, one of the reasons that we built this model end to end is we wanted this idea of a consistent, homogeneous inference cycle. In other words, unlike ChatGPT or Grok, FSD is a real-time system.
Yeah.
Right. It has to work in the real time in order to drive. I mean, it obviously could record information, and it could run at a different pace.
Yes.
But what real time means is it's running at the pace at which the car is encountering the environment, right?
When it makes a decision about 1/36th of a second, it has moved that 1/36th of a second into
action.
Into action. Yeah.
Yeah, because it can't be behind.
No.
Right.
No.
it could, for example, like imagine that they have a system internally where they record all the data off the vehicle and they try to run it through, and they're doing some new model. Let's call it version 18. I'm making this up, folks. Not breaking news here.
Yeah.
And they say, okay, we want to do all this other stuff, or we have all these other modules that we've kind of connected within, and then assume they've trained it and all that stuff. But they realize that there's no way, they don't have the compute on hardware 4 to do that. So they run it through hardware 4 and they get the outcomes, but it lags real time. So a minute worth of data and all of a sudden, it's out to an hour of decision, and then it just gets worse. And that's characterizing a non-real-time system. You don't worry about that in ChatGPT. You don't worry about that in Grok. It thinks, it answers, you wait. It is happening in real time, but it's not real time sensitive.
Right.
So this is very cool. I mean, I can't express how amazing this is, because not only have they characterized, in other words, not only have they built this interpretability in the model itself, the ability to look inside, to be introspective, to see how the thinking process is working, but they've also obviously built a small language model alongside so that they can ask questions in proper English,
right,
and get answers in the same. That's awesome.
Yeah. 100%.
Like this is like, blew my mind. Blew my mind. Did not know that they could debug the system like this.
Yeah.
Cool. So let's talk about what happened a little bit. We'll back out to the earnings call. And if you beg me, beg my pardon here, I'll read this.
Sure.
Elon Musk in the Q3 earnings call 4 days ago, said, we've released 14.1. We've got a technology roadmap that I think is pretty amazing. We'll be adding reasoning to the car. Our world simulator for reinforcement learning is pretty incredible. Our Tesla reality simulator, when you see it, the video that is generated by Tesla reality simulator and the actual video looks exactly the same. Doc shows examples of that. It's insane. That allows us to have a very powerful reinforcement learning loop to further improve Tesla AI. This car will feel like it's a living creature. That's how good the AI we've got on the AI4 computer before AI5, which is important. AI5, like I said, to some metric is 40 times better. Just to be safe, let's say it's a 10x improvement. So he's saying we will deliver not only have we delivered version 14, but they have an incredible roadmap. They built some incredible tools that allow them to do stuff that will deliver reasoning. They are using heavily reinforcement learning. I talk about that in my article. Ashok talks about none of that, but I talk about that in my article because it's just not his topic he's talking around the edges of it because all the components of the stuff they've done in terms of building the real world simulator is necessary for reinforcement learning. Okay. And what reinforcement learning is in a nutshell is the ability to train the model. We go from human to superhuman, right? Human is we've done imitation learning. We've trained off of human data samples. We only do as well as the best of humans that we've selected. We've selected the best driving samples. We train the system on that. It performs that way. To get beyond that, they have to take it beyond human native data. And they have to do this. They use this technique called reinforcement learning. And the idea is that they set up the car. And when I say the car, I'm talking about a virtual car, something that's running in the cloud, something that's running in simulation. And they're using inference. They're in fact using the actual compute of the inference chips. They've got hardware 4 boards sitting in the data center alongside the rest of the NVIDIA GPUs, and they're running these trajectories, and they're scoring them, and they're letting the car train on the trajectories that gets the highest score for the desired outcome. I talk about that in the article.
And I hope that the desired outcome is not to make as many paper clips as possible.
Right. No. Yeah. The
I'm
desire.
that might be a little of an obtuse reference, but it's one of the things we worry about in the future with regard to these systems. But it's just a joke, just a joke. Okay.
Yeah. 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 No, I mean, desired outcome, of course, is in that particular scenario is to drive fluidly without collision, very safe. And what's really interesting about this is he talks a lot about, you know, we built this end-to-end system because, if you read some of my previous articles, when I was guessing into the box, I would have told you, actually, in sort of weird way, I'm right, but I didn't realize at the time what I meant by it. Is that there is a perception block and there is a planning block. And perception means understanding the world around you. And that's that whole...
Not just seeing it, but understanding it.
Yeah, labeling every dynamic and non-dynamic object in the scene. And then, Ashok has different terminology for that, the 3D Gaussians and all that kind of stuff that you saw in that one slide a couple back. And yes, they're doing that. It turns out they are doing that, but they're not building that block separately. They're training that block with the planning block.
Yeah.
And planning means, what is my next move? Based on this data, what am I supposed to do? And what they're doing is they're basically combining that in one single training kind of model, one model. In other words, what he basically is trying to say is, as long as we can preserve the end-to-end gradient. Now, this is a kind of very technical thing, but what he's saying is, when we try to walk through this model and compute outcome, when we back propagate, that's the step where it changes or nudges the values in the model to kind of meet the objective of the proper outcome. They call it minimizing the loss. Okay. There's like a loss. There's this thing that's kind of known in AI neural nets training as the loss function. And the loss function basically says, just think of it as a function that says, how far off are we from the optimal result?
Right.
Whatever the problem, how far are we off from the optimal result? And if we can characterize that, we can now back propagate through the model, change our values such that we can minimize the loss on the same sample going again.
So again, I'm trying to bring this down to the human level. If I'm shooting darts and I am trying to score, I have a process. I'm telling my arm to go at a certain level. I've got muscle memory that's telling my arm to go at a certain level, certain speed, and then it hits or doesn't hit what I'm shooting for. And now that's a negative reinforcement. It says, nope, you were not optimal, but
Right.
you're only off by this much.
Right.
That goes back through the brain neural network and says, okay, next time you take a little speed off and you'll probably get there.
Yeah. Yeah. I mean, you can think of that as sort of equivalent of training Optimus in this regard. Because, I mean, think about Optimus throwing darts.
Sure.
No, that's a really good one because what it leans to is the part I wrote here is that, the model generates intermediate reasoning tokens, and that allows for introspection, meaning debugging, trying to figure out why it did what it did. And then it allows us to take that kind of reasoning and feed it back into the model as input. And a good way of thinking about that, using your analogy, is that instead of it training from a reinforcement point of view, you were essentially describing it as the reinforcement learning of throwing the dart, throwing the dart. But this would be a little bit more like this. You threw the dart and you had a little thing in your ear and it said, you leaned too much forward, or you did adjust these 5 things. So that's feedback. And then you can imagine your next cycle picking up the next dart throwing it again, and you make those adjustments, and it can say, okay, then you've gotten closer to the target or the center, and then you're still off by something, and it gives you more feedback.
Right.
So you can make those adjustments. And then the other part of this, of course, is that it's very expressive that they built a small mini LLM into the thing for natural language processor that we saw in this example. So now I want to express this as to what's really happening.
Okay.
I mean, in terms of, at the end of the day, we talk, one of the things I noticed about AI is so much effort in writing and conversation talks about the training. We talk a lot less about the actual running of the thing.
Yeah.
Which is referred to inference as inference.
Right.
And that's, I think, that's where it all lives. So it's sort of important. And this slide does a bunch of things. So let me kind of go a bit slow through it. The first thing important to recognize is it's merging FSD and Optimus in the same slide.
Okay.
And what I'm saying effectively is that the inference of FSD and the inference of Optimus are or will be the same. And that's the big, that's kind of a big statement. That's what my Series 8 article talks about. Let's take a look at kind of the control flow here. And I'll go slow enough where there's not it looks like there's a lot going on here. It's sort of simple to understand, frankly.
Yeah.
On the left, you have the sensors that are input for both systems. So in the case of our vehicles, it's cameras, kinematic data like IMU, GPS, and audio. They bring in the audio signal and they use that to determine whether they hear police or fire sirens or so forth, right? And of course, the biggest amount of data is, in fact, the visual data coming off the cameras.
Sure.
And so this would sort of be a way of describing those, minus certain aspects of input, like the navigation data that is happening. This is essentially saying, in a nutshell, this is the 2 billion tokens on the input that we talked about earlier. And that runs through the middle. We'll just leave the middle as it is for a moment. And it outputs controls. And in the case of FSD, Ashok properly said that it outputs 2 tokens, probably a bit more. But effectively, steering angle and whether you're positively accelerating or negatively accelerating, right? So whether you're going to apply the accelerator as for that purpose, or you're going to apply braking or regenerative braking to slow the vehicle. And then on Optimus, of course, it's a bit more complex. Instead of, like, if you think about the vehicle's like 2 degrees of freedom.
Yeah.
Describe it. It's been described that way, yeah.
Yeah.
Whereas Optimus is both on the hands, and if you get total packages, many degrees of freedom. I don't know.
22 just on each hand. So that's 24.
And then you've got to add elbow
Hip,
joints
legs, and
legs, feet, body, head. But so Optimus is a lot more complex control output. Our outputs are, the tokens that output for controls in Optimus are much more complex. So now let's look at the middle here. I'm showing you 2 AIs. The first AI, the action AI, that's FSD. That is FSD version 14. The interactivity AI does not exist, but it will. And we'll talk about what that is. So the action AI is doing exactly what we know it does. We takes in the sensor data, outputs controls, runs through this neural network. The action AI is a neural network. And in the process, it outputs intermediate values, tokens, reasoning tokens, that essentially it explains itself.
Right.
It says what it's recognized and what it's recognized and why it's done what it's done. And it takes that data and other data and recycles it through the inference process repetitively. This cycle from data to controls is happening in your vehicle on hardware 4 36 times a second. Okay. The interactivity AI is something that is coming. That is essentially Grok in your vehicle.
Mm-hmm.
What this means is that now we have like a much more rich language model that has a lot more connections to a lot more pieces, general knowledge, systems outside the vehicle, etc. And it also has a way to interpret the audio signal for speech to text. So there's a block that converts speech to text in the AI, just like if you're speaking to Grok on the app. And then, of course, so you notice that when I show the sensor input, I show audio,
Mm-hmm.
but I'm saying audio goes through the action AI,
Mm-hmm.
but it also goes through the interactivity AI, kind of at the same time.
Sure.
Concurrently, sorry, I was thinking of the term. Concurrently is being, pushed in two different directions, because sometimes the audio needs to be recognized as the owner or a passenger in the car speaking to the car.
Right.
And by speaking to the car, then there's this interpretive block that's essentially what we would think of today as Grok itself or the LLM. Now, I would suggest to you that it is the technology of xAI, but not the full model, right? Mm-hmm. It comes down to the car in a smaller package, and that package is interconnected to the vehicle's controls, and so it understands what it knows about the vehicle. Just like I said before, how Grok knows about the contemporary post happening on X. Mm-hmm. Mm-hmm. This interactivity AI needs to know about what's happening with the vehicle. So this is a way to say that the interactivity AI is essentially the user interface to your vehicle or Optimus. Mm-hmm. And that is that you speak to it. Mm-hmm. And it speaks to you. And in the process of doing that, it sends in requests to the action AI to do things. So, for example, you might say to the car, speed up. Mm-hmm. Mm-hmm. And the car can speed up. Mm-hmm. Or don't take this exit. Now, maybe the routing system wanted it to take exit 4A, mm-hmm. but you're looking at some situation in your brain or whatever you're thinking. You're like, I don't want to take that. I know it gets really jammed up or something. Maybe the system isn't smart enough to know it at the time. So, go take 4C. Mm-hmm. So don't take 4A, take 4C, even though you see it on the, routing. Or you can ask a much more, deep planning question like, how many minutes to the airport? Mm-hmm. 42. What road are we taking? We're taking 101. What if we take 280? Well, that's 47 minutes. Okay, take 280 instead, because it's much more relaxing or scenic or whatever, whatever the reason that the human. And this is also the interface through which, when robotaxi at scale, this is how we will interact with robotaxi.
Right. Yeah, and I think it should have different levels of snarkiness that you're allowed to,
yeah.
You say, listen, I'm perfectly fine with the bot being very snarky. So, you tell it, hey, you should take A4 or B4, whatever, instead of what you're going to do. And it goes, what are you, nuts?
Yeah. Well, I mean,
that's a really bad idea.
in a slightly less humorous way of thinking about it. No, seriously, it could come back and say, no, I got you. The traffic isn't what you think it is.
Yeah, right. Yes.
Like you're used to that pattern, but that's not developed today. I've already got eyes on that through the.
That's what I'm saying. Different levels. You could have the snarky level. You could have the calm level.
Well, I mean, in a different way of thinking about it too is we see these different modes that have developed from sloth and hurry and Mad Max on the vehicle. And frankly, those modes are a collection of smaller sub-preferences. Like Mad Max, there may be 12 to 15 to 30 different little sub-components like offset or lane change dynamic, like how much room I need for a change between, offset to the previous, to like braking dynamic, like how hard is the customer willing to I'm not saying it right. How much, how much force on, how hard should the car brake?
Right.
That you're comfortable with, right? And so you right now you're tuning this with I think there's 5 different ones, but really there's a bunch of little sub things in there. And if you kind of tease them out, all of a sudden they feel like, wow, you can really make this car, as Elon would say, sentient, because now you're not only a couple things about, you notice that in this box here, I show reasoning tokens like going down towards the interactivity AI, because of course it needs to know what the car's doing, but also looping back into the action AI.
Yeah.
And that is because the full expressiveness of this might lead to, I think, an example that Elon gave in the earnings call where he said, the car comes into a mall parking lot and you have expressed a preference to park the car far away from a bunch of other vehicles because you're not looking for door dings. You want the corner spot in the far reaches of the mall parking lot. But your car, which drives itself, doesn't need to bring you to that parking spot. So you say, where are you going? And the car says, I'm going to one of those corner parking spots. And you say, no, go to the front door of Macy's and drop me off, and you go park yourself.
Yeah.
Okay. There's a lot of stuff happened there if you want to unpack that, but there's a lot of stuff that and including something that we don't really talk about here, which is the recording of preferences. The recording of your, so the next time it does that, it says, I'm going to go drop you off at the entrance to Macy's if that's what you want. And you say, yeah, go for it, because it's taken in that data. And by the way, that's how we as humans would evaluate how sentient the creature is, in the sense, did it learn from previous behaviors and interactions with us to create something that's more fluid and doesn't create that high friction interface to us, that every single time it shouldn't ask us the same questions if it kind of understands. And the question is, does it understand truly what you're trying to do? In the case of maybe one day you say, drop it off at the Macy's entrance because you've got to return at Macy's. But generally speaking, you don't want to do that because that's not the store you typically shop in. So you want to be dropped off at the main entrance of the mall. You expect the system to ultimately start to figure that out.
Right.
But in order to get that full expressive sentient reality, you need this other component, which I call the interactivity AI. And I think that tech stack, if you will, comes from XAI. But if you were to subtract it, there's a lot really in that action AI and this output of reasoning in a loop that that can make the car feel just quite alive, I believe.
Right.
And just to be clear again, this diagram is the inference framework for vehicle or Optimus.
And Optimus, right? Exactly.
Yeah. So it's not architecturally. They're doing the same thing.
Yeah. No, that's the beauty.
Yeah, and that is the beauty, and that is what I talk about a lot in that Series 8 article. I'm saying that they're unifying these architectures, folks. They're unifying these architectures. They've got all the piece parts to do that. They're built up the data pipeline, the simulator, the reinforcement learning. I mean, if you saw way back in the very first slide, I showed a picture of Optimus, the simulator generating the interior of the Tesla factory from Optimus' point of view. So it had originally taken in data from the Optimus bot's sensors, its eyes, held that as a template through which that then they put through the simulator, and they said, go ahead and generate, a walk left or right down these aisles, and it guesses what's coming, and it could add other people in the factory, et cetera. Just like the vehicle simulator. If folks go through the Ashok's presentation, he has some really great videos in there where he literally goes in and he shows the simulator generating a city scene, and absolutely impossible to tell that that's generative.
Right.
And it's not only generative, but it's happening in real time.
Mm-hmm.
That's quite incredible. It's happening in what I call real time on AI4.
Right.
In
the 10 times better coming in AI5.
Yeah, no, it's super important that, Tesla continue to make progress, because, one of the things that I see a lot when by the way, I think we can just kind of stop the talking here. This is my, banner slide. Says I write a lot of stuff. Go read it.
Yeah.
One of the things I see that occurs a lot is there's this model in people's brain about FSD is, what version is the version that is the version?
Mm-hmm.
Like the one that arrives that we declare is autonomous, can go unsupervised, can go on robotaxi. And the answer is there is no such thing. There's a version through which there'll be another version, through which there'll be another version. And, if you go back 2 slides here, what does Elon say? We're adding reasoning the car. Sorry. We've released 14.1, got a technology roadmap that I think is pretty amazing. So 14.1 is a thing.
Yes.
It's on the car right today. It's 14.1.3 is present on some folks' cars. It's the current released version of unsupervised. But they've got a complete roadmap here of what they're doing. They're adding reasoning. They're doing this. They're doing that. So it's pretty cool stuff if you think about it. And so I think that no one should think of it as the endpoint. It's just like iPhone. There's been I don't know how many. There's one major software release a year, and then there's a bunch of minor improvement. Some things that fix bugs, some things that add kind of follow features through the year, and then next year they drop a new big version. And the same thing will be probably true of FSD as it evolves, and some of those things will be in the box of it got safer through more. That Niagara Falls of data has informed some use cases that weren't seen before and were triggered by the system saying, here's a piece of data that the system had suboptimal performance on. What's really incredible about what's happening here with Tesla is that they're using their own system to improve their system.
Right.
I mean, we need to really think about what that means, because it means a couple things. It means that, of course, it means the system improves, but it means that it improves at an exponential rate that's beyond what the team can sit down and do. It's just sort of improving itself naturally. And it's doing it because it's not just because they have the fleet data, but that's such a huge thing. I mean, 500 years of data per day recorded, but it's also because they built the entire infrastructure, right?
Yeah.
They have this, in that article, I start with the lead off that I actually say, this is kind of boring or table stakes, but they built this thing that I call the data pipeline. And it's an important concept. It basically says they know how to select, move, process, store, fork to simulator, push to reinforcement learning, push to model training, push to release, and they know how to do this at scale.
Yeah.
And since they've done that with FSD, they're applying it to Optimus.
Mm-hmm.
And so today, I think the way you can think about it is FSD is kind of the lead-off project. It's the big thing, and Optimus is the follow-on project, which is very similar. It's a vision-based reasoning system, blah, blah, blah. It has to go from photons in to controls out, very similar things. But it's the mini project in the corner, it's the thing that's the big, the daddy project, of course, is FSD, but that's not going to persist. That is not going to persist. What's going to happen is, and by the way, they're both under the same VP here.
Right.
That's something that happened a couple months ago. And because they are unifying these things, they've talked about it openly. It's not just me saying they're doing it. But these things are coming together where Optimus isn't the child project. It becomes, equal to and bigger than, in a sense, a good way of saying this is that there is many more moving parts to Optimus, and there's many more places it moves than the vehicle. Yeah. The vehicle is a very confined object, right? It travels on well-defined roadways, and it really only has 2 degrees of freedom as output. Optimus, on the other hand, can go pretty much anywhere that it can fit, right? Meaning it can go in homes, it can go in cars, it can go in elevators, it can go in subways, it can go on planes, it could go, on boats and so forth. It can go and explore the world as it sees it. So it's got a much more expansive input stream, and it's got a much more dynamic controls output. So in a sense, it's the one that's it's the one that probably owns the problem in the end.
Yeah, super true, super true. All right, so now we understand how reasoning works and why reasoning is going to make a big difference in the way that Optimus and the car work. And I think there'll be more. I think we'll be going past reasoning to whatever's next. And I have a suspicion that the next thing after reasoning is going to be really, really close to AGI. And although I think reasoning will get us pretty close by itself, but it'll be what I was looking at the other day, Phil, was the combination of reasoning and memory. I don't think anybody's been talking about that.
Yeah.
Memory was an amazing addition to the stack in terms of using Grok on it. I use Grok, multiple times a day to write things for me, to research things for me. And it's one thing to have, its amazing capability to do the research and to use reasoning in that research, but then it remembers what I've done.
Yeah.
Remembers the book. I had the entire manuscript for the book in there, and I would say, okay, that's the manuscript. Now, what do you think I should do about the title? What do you think we should do about where we sell it?
Right.
I didn't have to go back and put the manuscript in over and over and over again.
Yeah.
It had the manuscript, and it knew the interactions that we had going on with regard to it. So and then it could reason from there.
Right.
So it's kind of the combination of the two is pretty important.
What's incredible there is it's taking this manuscript, 300 something pages of text. I don't know how many words. You probably know the word count.
80,000, something like that. Yeah.
Okay. 80,000 words, call that 100,000 tokens for, because the token to word mapping in an LM there's more tokens than words because it's subcomponents of words sometimes. So call it 100,000 tokens, which, by some measure isn't that big for an LM these days. But I mean, 5 years ago, that was insane. Yeah. But it's taking that data, and every time you ask it that follow-on question, it's shoving it back through the system.
Right.
And why does it have to shove it back through the system? Because it's dispatched that, if you think about what's happening, every time you ask a question. So for example, you put that entire text in there and you say, who's the coolest author? Who's the best storyteller? There's some really clever stuff I did there just to see sort of how it stack ranked people in various different dimensions. And it was fun to play with it. But who told the best story, or who did this, who did that. And so what happens is, once you kind of tee that up, that question that you've asked along with the manuscript gets pushed off to some GPU in the data center. Wherever that data center is. In this case, it's not like Grok inference is not being done at Colossus. That's where the training is done in Memphis. It's probably running in Oracle's data center or something, so it's dispatching off to that interpretive, it's going to some GPU somewhere. And the next time you ask a follow-on question, it's not going to that GPU necessarily. It may have some GPU affinity, but it doesn't need it. It's just sending the data to the next GPU. Yeah. And so that GPU is like, oh, what do I need to know? What kind of memory do I need? What kind of context do I need to reinstantiate? Well, it's all coming through the prompt. But the idea of having a kind of a more permanent memory is more interesting, in the sense that imagine you go back a year from now. Yeah. And you say, I was asking some questions about that author, Phil Bessle, in this article. Has Phil written anything recently? And has he made any improvements on his data chapter? Well, it has the data chapter somewhere. Where? It's stored somewhere. It brings it back into context. It, sort of takes it out of the refrigerator, defrosts it, and puts it on the table again. We should expect that to happen in FSD on our cars.
Right. Now, now let's be realistic. It doesn't do what he just said yet.
Right.
It has a limited amount of memory.
Right. And it's normally what we'll call session-based memory. But eventually with, say, FSD, we will expect, and actually it goes really beyond that, Randy. Think of it a different way. If you arrive in Austin at the airport, you pick up a robotaxi, you get in the robotaxi, and you go somewhere, downtown, convention center, or wherever, and you ask it to stop somewhere or do something, or you tell it, don't go down first, or whatever. Not only can it build a memory of that, but that memory lives with you, not that robotaxi. It lives with you, the customer. So the next time you arrive in Austin and you get in the airport, and the next robotaxi picks you up, it brings that memory alive. So the next robotaxi you're in knows your profile and uses your memory interactions with the previous robotaxi. And wherever you go, whatever you do. So if you arrive in Miami and you take a robotaxi around, and you've expressed some preference in Austin 2 weeks earlier, that travels with you.
Yeah. Okay, Phil. Well, I think we've covered it today, and
that's a lot.
That's a lot. Yeah, no, it's good, and very, very illuminating. And so you need to tell them what to do. Do they need to do anything specific with regard to some book or something?
Yeah, go buy that book. I think it's a good book. I think it's a really good read for people if you're trying to catch up or understand where we are with AI today and how profoundly it's going to impact our lives and our children's lives and so forth, society.
And a lot of practical how to use this, how to do this in your company, how to do this as an employee, how to do this as a manager. I mean, there's
it's sort of like what you can do with it now, and kind of leaning in on how it's going to impact you and others in the future, and how you can be prepared for it. Because it's, I think this is one where, we're used to, the last 20, 30 years, we're used to new technologies coming on the scene, and we think of them as having impact in our lives, but we don't think of them as having profound impact that is both amps the level of opportunity and fear, frankly.
No.
This is one where I think we're on that bubble, so it's a bit more something people need to engage in, I think.
Yeah, and you can count on the fact that it will be an optimistic book because I am the lead author.
That's right.
So, again, thank you, Phil, and to all
Yeah.
of you out there. It's been great talking to you.